And then I guess we also have like a lot of competitions and things going on, but that's no problem at all. I'm so grateful that you all decided to join me today. And I think today we're gonna have, I guess like a lot of fun. We're gonna do, like I said, we're gonna kind of continue the modular arithmetic part of our class. So we're gonna do a lot of problems today, using some of the lessons we learned last week. And today I think we'll kind of introduce you guys to some problems that like you can't solve using just patterns. Because I know that was something last week. You guys were like, give me a challenge problem where like I actually have to use what you taught. So yeah, that's what we're gonna be doing a lot of today. Hopefully we'll get to go over like a recent competition problem. We'll see. But yeah, I think it'll be really good. So I guess like on that note, we'll go ahead and get started with our icebreaker. So our icebreaker for today is what is your dream destination? Oh, also, for those of you guys who are also in our algebra class, the reason why we didn't have an algebra class this week was because I had an FBLA conference, so I was out Monday and Tuesday for that. I got back yesterday evening, so I'm here for this class. But yeah, that was super fun. It was my last fall leadership conference for FBLA, so that was really nostalgic, a little sentimental for sure. But to kind of make up for missing that class, we'll do one class. Over Thanksgiving break for algebra. So that'll be on next Monday, but there will be no class next Wednesday, or sorry, for geometry. And there'll be no class next Wednesday for algebra. Okay, cool, cool, cool. Just wanted to make sure we kind of all know that. Cool, cool, cool. Okay, so let me see what you guys are saying so far. Cypernese says a huge blanket is the dream destination. Wow, not exactly the answer I had in mind, but like I guess points for creativity. Yeah, so we'll say blanket. Bed. Okay, wait, I feel like bed is better than blanket. I'll put that. Again, not exactly the answer I had in mind, but that's a okay. Let's see. Oh, Cypher says my friend is an F. Yeah, a cool club you all should totally join. Amari says Italy because I love Italian food, an excellent answer. Or Jamaica because my dad's side of the family is from there, but I've never been there. Okay, that's super duper cool. I have been to Italy a couple years ago. It was very nice. Very lucky to go there. But they do have amazing food. Okay, well, okay. So they have good food. But if you get bored of like pasta, cheese, and tomatoes, like you will be very sad. Because that's kind of honestly all they have to eat. But it's okay. Like it was very pretty, very nice. So yeah, I think Italy is a great destination, Amari. And Jamaica sounds really, really cool too. Getting to see like the family and everything. That's awesome. Jason says Universal Studios. Yeah, I haven't been to Universal in so long. I feel like I've gone to Disney more often. But yeah, Universal is a good answer. Amari says, I'm in TSA as a theme champion. Ooh, that's really awesome. Congrats, Amari. That's super cool. Sumhit says, Hyderabad. Awesome. Hyderabad. Yeah, this is a city in India, in case anyone is unfamiliar. Hitharth says, the Bahamas if we're talking vacation and also with friends. Very nice. Oh, oopsies. Bahamas. Awesome. Tanvi says Japan, Paris, London, Italy, India. Let's see. Saudi Arabia, and I think you mean UAE. But yeah, wow, all really great options. Oh, wow, I just combined options and destinations together. That was super weird. All really good options. And I think these are definitely really big tourist locations. So definitely lots of stuff to do here. But it looks like you have a good list on these. So maybe traveling is in your future. Sai says a utopia. Ah, very neat. I don't think a utopia exists. I think it's purely hypothetical. But we'll see. Maybe it'll exist one day. Let's see. Mari says the variety in Italy isn't there, but it's still good. Yeah, I agree. It's still good food, but like I don't know if it's something I can eat every day. Like I'll get very bored. I think in terms of variety, I feel like there's a lot of variety in maybe like Asian or East Asian foods. But I feel like a lot of like Western foods are very similar. Like there's not a lot of variety. It's like based on the same stuff, I think. I don't know. That's what I would say. But yeah. Let's see. Oh, some hit says a Takis factory. Okay, wow, that's a definitely a diverse answer. Takis factory. Cool. What else do we have? The Bahamas. Awesome. Disneyland. Oh, good answer. Oh, that was scary. It's like something on my desk. Ew. Okay, sorry. Disneyland. Disney. Wait, is this the one in Florida? Or is this the one in California? I can't remember. Which one's in California, which one's in Florida? Like, I'm not very sure. Oh, I think someone had asked the same question. We're getting an answer. Some it says any beach house, Panama City Beach, a good one. PCB, I will put. Um, cool, cool, cool. Japan from Bovit, Tokyo from Sumhit. Yeah, Tokyo's nice. I think Tokyo is like the largest city. I'm not sure though. The Lego Factory. Oh, good answer. That's awesome. Ooh, Canada. Yeah, Canada's gorgeous. They also have really nice cherries. I think we did like a road trip to Canada when I was super young. And we stopped like near the border and they had good cherries. That's like pretty much all I remember. Um, okay, cool, cool, cool. Wow, lots of discussion about Canada, which is awesome. That's great. Cool, cool, cool. The M&M factories. Awesome. Wow, I see a lot more like food places, which is really funny. Disney World. Okay, so you have Disneyland and Disney World. Let us see what the difference is. Uh, Hold on. This is like anticlimactic because I'm still catching up with all your guys' answers. Crayola Factory. Ooh, Six Flags is good. But I have been to Six Flags so many times for FBLA that I'm just like super sick of it. Like I'm just like, I feel like I could use a break from amusement parks. Okay, cool, cool, cool. Atlantis. I think it's Atlantis. Yeah, it should be Atlantis. Yeah, that is also mythological. Atlantis. Awesome. I think Yeah, I think Disney, oopsies. Chipotle, that's a good one. Okay, well, I think we have a good variety here, which is awesome. Let's go ahead and kind of transition. So, in the past 2 weeks, I don't know. We had the AMCs, so I'm not sure if anyone did those because those are AMC 10 and 12, and most of you guys are still in middle school. Um, so we'll see. But yeah, I think we'll do like one potential question from there. So yeah, just like maybe keep an eye out for that. Um, okay, awesome. So let's go ahead and get started. We're just gonna do a bunch of problems today. I'm not really gonna like teach you guys new content. Everything that you guys need to know to solve these problems we talked about last week. Okay, so let's go ahead and get right into it. Our first problem is what day of the week is it 100 days after a Monday? I'll give you guys maybe 30 seconds to 1 minute to think about this. And we'll kind of talk about it from there. Okay, awesome. I think I see a lot of people saying Monday, or sorry, Wednesday, which also happens to be today. Okay, that was actually kind of a coincidence that that was the answer. But let's see, who, maybe I feel like today, because we're doing a lot of problem solving, maybe I'll like call on more of you guys. So I think the first person I saw who said Wednesday was, Coven. So Coven, if you would like to unmute, go ahead and share how you got to the answer of 100. Or of Wednesday, sorry.
I did 100 divided by 7, which is 14. And then we have a reminder of 2. And 2 days after Monday is Wednesday.
Okay, perfect. So 2 days after Monday is Wednesday. Okay, awesome. Thank you so much, Coven, for unmuting and giving us an awesome explanation. You are 100% correct, which is awesome. Okay, so a couple of things. I think this is like the main idea, right? There are 7 days in a week, and the weeks like cycle, they cycle around, right? So we want to find out like how many times 7 goes into 100, and then take those leftover amount of days, and then kind of just add them to the day we are currently on to see like where our next day is. Okay. So the reason why this relates to modular arithmetic is because we're dividing and we're using the remainder. So we're working with remainders. Remember last week when we talked about modular arithmetic, we said it's like the study of remainders, right? So because we're dealing with like this remainder of two and we're using it to solve a problem, this would be classified as modular arithmetic. Now, if I wanted to write this in terms of like the notation, I would say 100 is congruent to 2 modulo, oh, I don't actually write modulo 7. Okay. Is everyone okay with like the fact that these two are the exact same thing? Because I'm going to start using this notation a little bit more. So I just want to make sure we got a quick refresher on what everything means. Okay. Perfect. I think a lot of people are saying yes. So this is good. Glad to see that. Let's go ahead and move on to our next question. Okay. So you guys might still, so we're still kind of like in that easy territory. Maybe this one is also easy. Maybe you guys might see, maybe you guys might still use patterns. Maybe you guys might be convinced to turn to modular arithmetic. We shall see. But yeah, let's go ahead, spend a couple seconds on this problem and see where we can go. Wow, okay, I already have an answer from Hitarth. Awesome. Let's see if anyone else agrees or disagrees. Okay, I think Coven agrees. And so does Jason and Rohan. Awesome. Okay, Hanvi and Samhit as well. Okay, awesome. Oh, and then Sean also agrees. Okay, good. So I think we have a lot of agreement. I'll go ahead and ask Hitharth if you would like to unmute and share why you think two is the correct answer. Please go ahead and do that. We'd love to hear your solution. Oh, you don't want to talk. Okay, no worries at all. No worries. Who did I see next who put in an answer? I think Kevin put in an answer next, but since he's already spoken, I want to make sure everyone has an opportunity to speak. How about Jason? Jason, do you want to share how you got to two? No. Okay, that's okay. So that's all good. That's all good. I think Hitharth is actually putting a solution in the chat. So let's see if we can go ahead and follow that. Hitharth says, so basically every power of two ends with 5. And 7 over 5 equals 1, remainder 2. Okay, awesome. All right, let's see. This is interesting. I wonder why we're taking powers of 2, but we're dealing with a 5. Where is that coming from, Hitharth? Let's take a look. I think I kind of like where this like 2 stuff is coming from, but I think oh, every power of 5 ends in 5. Okay, cool, 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 cool. Sorry. I was like a little confused there initially. But yeah, okay, so that's a true statement. That's a true statement. But we can't necessarily look at the units digit because remember, this is like a remainder of 7. So 7 and the units digit have no relationship, right? The only time we can really look at the units digit is if we're dealing with modulo 10. So I think like there's a couple ways to go about this. The first way, and maybe this is the most easiest to understand, is to just say like, oh, I can look at 5 to the power of 1 is congruent to 5 mod 7. And then 5 to the power of 2 is congruent to 25 or 4 mod 7. And you kind of just like keep doing this and figure out like where the cycle is. I think maybe like another interesting way to do this is to recognize that 5 is actually congruent to -2 mod 7. Okay, and actually, when we do negatives, we don't actually write the negative sign. Okay, so this is like really weird, right? Like, how can you have a negative remainder? The idea is like what we're doing is to get to 5, we do 7 minus 2. So actually, like in this case, we're saying, remember, like a remainder is like you do like 7 times your quotient. In this case, your quotient would be like 1, and then you add your remainder, so negative 2, and that's how you get to 5. So a really nice thing about like modular arithmetic that kind of extends remainders is the fact that you can have like negative like values, which is not always true of remainders. So this is like a very powerful tool, and we'll kind of see why in this question. Okay. So we have 5 is congruent to negative 2 mod 7. Is everyone like convinced that this is a true statement? Like I'm not doing like voodoo magic or something. Like this is true. Is everyone okay with that? Yes. Okay, good, good. All right. So we have 5 is congruent to negative 2 mod 7. So now our problem has turned into 5 to the power of 100 is congruent to negative 2 to the power of 100 mod 7. Notice that this results from one of the properties we talked about last week. And then also notice how I actually have included the parentheses this time. The reason why I did that is because whenever we're raising a negative value to an exponent, we have to put the negative value in parentheses to make sure that like negative sign is like considered the right way, okay? The lucky thing is because we have an even exponent, this negative sign will actually just become like 1. So it doesn't even matter at the end of the day, actually. So we can say like 5 to the power of 100 is congruent to 2 to the power of 100. Is everyone okay with the fact like how did we get this? Is everyone okay with that? Yes. Okay, awesome. So now's the easy part, right? So like we want to figure out like what is 2 to the power of 100 mod set. Oh, okay, never mind. AS says no. That's A-okay. So let's go ahead and figure like kind of discuss like where this is coming from, right? I think probably the trickiest step is like 5 is congruent to negative 2 mod 7, right? So let's kind of like redefine what this means. So think about like what it means to have a remainder. Let's say you're doing some like division problem. Let's say you're doing like 28, or we'll do like 25 divided by 7, right? Because that's like kind of over here. 25 divided by 7. We know like this will go into 7 will go into 25 3 times, and you'll kind of get like a remainder of 4, so R4, right? So 25 is like 7, or sorry, is like when divided by 7 is like 4, with remainder, or sorry, I switched it around. 3 with remainder 4. Okay. And so when we try to like express this in a way, we'll get 25 is equal to 7 times 3 plus 4. So when we're dealing with remainders, we typically just add them, right? So it's the same thing here, except when I'm doing like um 5 divided by 7, instead of just like leaving it as a fraction, because technically 5 is congruent to 5 mod 7. Instead, what I'm doing is I'm saying like, oh, pretend the quotient is 1. So then I get 7 times 1. But to get to 5, I need to subtract 2. And so because I'm like doing the subtraction, this is basically like adding a negative, right? That's what subtraction is. So I'm saying like this negative 2 is my remainder. Because if I do like plus negative 2, 7 plus negative 2, that's going to be equal to 5, right? So this still holds. So this is definitely like a little backwards, the fact that you can have a negative remainder, but this will be a true statement in terms of modular arithmetic. So then we kind of like work our way down here. We get this equivalent expression, and these two are basically the same thing because notice this negative sign will kind of like become 1 because like you can rewrite negative 2 to the power of 100 is equal to negative 1 times uh, yeah, negative 1 to the power of 100 times 2 to the power of 100. And negative 1 to the power of 100 is just 1, because like if you have an even power for a negative number, that negative sign will go away. And so you're just kind of left with 2 to the power of 100. Okay, so that's why these two are congruent. So that's like kind of like the long-winded explanation for that, but hopefully that helped. So let me go ahead and clean up my screen a little bit. We don't really, this is like an example. It has nothing to do with the question. I just wanted to make that clear, like why this is a true expression, because it is definitely a little wonky. All right, so now we have 2 to the power of 100 mod 7. So what we need to do now is do some simplification. So 2 to the power of 100 mod 7. All right. I think like maybe we talked about this last week, but if not, I think something important to notice is like 2 cubed is actually congruent to 1 mod 7, right? This is like pretty cool. This comes up a lot. The fact that like 2 cubed is has a remainder one when divided by 7. But I think it's also something you can see like by observation because 2 cubed is 8, 8 divided by 7 is 1. It's a pretty neat, right? So what we're going to do is we're going to say 2 to the power of 100 is equal to 2 to the power of 3 cubed times 2. Okay? Um, is everyone clear like how these are equal? All I did was kind of like these um, break up this exponent. And the reason why I broke it up like this was because I know like what 2 cubed is congruent to mod 7. And so I want to try to get as many 2 cubes as I can because that'll make my life super easy. Okay? And so now that we have this, if we want to find 2 cubed mod 7, well, lucky for us, this is actually, ooh, I did not want to squeeze that. This is actually going to be congruent to um, 2 cubed to the power of 33 times 2 mod 7. Okay. We already know, and we can kind of like use our rules from last week. We already know that 2 cubed mod 7 is actually equal to 1, right? So that's shown by this property like down here. So what I'm going to do is I'm going to say like this entire thing. Actually, hold on. Let me like move this up here just so like it's clear. Okay. It's clear that these are related. Oopsies. What did I like miss? I like missed a piece. Okay, there we go. Okay, sorry about that. So this like we use this fact like here. So then we say that this is congruent to 1 to the power of 33 times 2 mod 7. And 1 to the power of 33 is just 1, right? So like nobody really cares about that. We just get 1 times 2, which is 2 mod 7. Okay, so if you kind of like trace this all the way back, we see that 2 to the power of 100 is congruent to 2 mod 7. And we know that 5 to the power of 100 is congruent to 2 to the power of 100 mod 7. And so that means that all of this stuff is all equal, meaning that 5 to the power of 100 is congruent to 2 mod 7. Okay, so that is our final answer. So good work to everyone who got this question right. Um, I do see one question in the chat from Coven who asked, why do we have to get a lot of 2 cubes? Yeah, so the reason why we get a lot of 2 cubes is so we can get as many ones as possible and bring this 2 to the power of 100 down to something that's like pretty easy to handle, right? Which is like 2 to the power of 1. Ideally, we'd want to get rid of all of these. So we'd want to say like we wouldn't even want this, but we're trying to like obviously that's not possible. So we have to have like at least 1 2 left over because that's just the remainder when 100 is divided by 3. Okay, so that's kind of like where that comes from. Yes, let's do a quick recap. Okay, so starting off, okay, so there are two solutions to this. The first solution is you do your standard, like find your pattern and like do all your remainder stuff, and that's this pit over here. You can do that. I just chose not to because I wanted to show you guys like an application of like what it means to like go through this entire process with modular arithmetic. Okay, so if you're not convinced like this all works, go check it with this pattern finding thing. Okay. Um, the solution we're doing is using a direct modular arithmetic solution. So instead of dealing with like 5 mod 7 or like 5 to the 100 mod 7, what we did was we noticed we can write 5 is congruent to -2 mod 7. Okay, and we kind of talked about why this is true, looking at example of how remainders are like used and written. And so now that we have this idea, we can say 5 to the power 100 is congruent to -2 to the power 100. So all we're doing here is raising both sides to the same power of 100, which is true by our rules of modular arithmetic from last week. So now that we have this, what I've done now is I've gotten rid of this negative sign, and the only reason I can do that is because of the fact that I have like this 100 exponent, right? And an even exponent paired with like a negative base will actually just give you a positive value instead, right? So think about like -1 squared. -1 squared is 1. -1 to the fourth power is also still 1. So we're kind of still doing the same thing, except now we're just left with 2 to the power of 100 in this case, okay? So we know these two values are equal. So at the end of the day, I realized I have a little typo here. So at the end of the day, really all we need to find is what is 2 to the power 100 mod 7, okay? And that is what we are doing in green over here. So we know like we figured out like 2 cubed is congruent to 1 mod 7, okay? That kind of comes from observation. You'll kind of see that, okay? And so what we want to do is we want to try to get as many of these ones as possible because it makes multiplication super duper easy, okay? So to do that, we need to extract as many 2 cubes as possible from 100, and there's 33 of those. You can find that with division. So 2 cubed to the power of 33 times 2 is an alternate way um, to write 2 to the power of 100. So we're going to take this mod 7. Again, using our rules from last week, we know that this is all equal to 2 cubed to the power of 33 mod 7, which is also equal to like 2 cubed mod 7 to the power of 33. So we already know 2 cubed mod 7 is actually just 1. So 1 to the power of 33 is what all of this stuff comes down to, which means it's just 1. But don't forget, we still have that like little 2 hanging around, right? So we just have to drop that 2 down. We get 1 to the power of 33 times 2 mod 7. And this will obviously simplify to 2 mod 7. Okay, so that's where this final answer comes from. I'm gonna let you guys think about that, maybe process some of the steps in between for a couple of seconds while I look in the chat for any questions. Um, yeah. Bobbitt says this was confusing. Hopefully the recap helped. I know this can seem like kind of tedious, but I will say like sometimes there are problems where there will not be like the cycle won't end at 1. Like sometimes your cycle will never ever have a 1. So it's actually like really hard to just go about it like that. Because sometimes you'll end up getting like repetitive mods, which is definitely an interesting challenge. But in that case, like modular arithmetic is the only way to solve it. Like it's very difficult to do it the normal way without like repeating mods. It gets very confusing. Um, Also, I will say like, actually, never mind. I won't say that just yet. Yeah, no, I won't say that. Okay. Bobbit said 1 to the power is 1, but negative 1 to the power of 1 is negative 1. Yes, excellent, Bobbit. That is absolutely correct. Okay. Let's see. Some hits says, obviously. Nahal says yes. I'm sure that was in response to my 1 to the power of 33. Bobbit says, hashtag easy but long modular arithmetic. Yeah, it is definitely long, but I will say, like, a lot of modular arithmetic for, like, the beginning portion at least is definitely, like, a lot of working with remainders and things. So it's a lot of like notation stuff. Like you guys know how to work with remainders. A lot of this is like probably intuitive, but I'm just throwing in that extra notation. But I promise like this notation is actually like super meaningful going forward. And it makes life like a lot easier, right? Because this looks like an equation, which we are like trained very well to deal with. So yeah, this is like I think maybe a good example. And I think it gets faster as you do it. But that's true of any math concept. So yeah. Okay, NBT kind of gets it. That's good. The more problems we do, the more sense it'll make. Hitarth also kind of understands. Awesome, awesome. Oh, I think I meant to say negative 1 squared is 1. Sorry, sorry. If I messed it up, I apologize. Okay, Kevin asked, so then what is, an interesting question, although a tangent, but I'm willing to indulge, negative 1 to the power of negative 1. So this would be like 1 over negative 1, which is negative 1. Yeah, so that, oh, I wrote negative 11. So yeah, it would still be negative 1. That is correct. Okay, I'm just going to delete that. That was a good tangent. Oh, it shouldn't be positive 1. It should be negative 1. Yeah, yeah, yeah. Okay, stellar. Cool, cool, cool. So let's go ahead and do another question. I want to see like where's a good. Okay, yeah. Okay, okay, cool, cool, cool. Let me clear up my screen. Bobbit said yes, that is correct, Bobbit. Good summary. Okay, here is our next question. So kind of a different question. But let's see. Oh dear, I like broke something on my page. I don't know what I did. Sorry, guys, if I'm bothering you by moving the screen too much. I apologize. Okay. Let us see what everyone is saying. Bhavit says two. Someone says I did this in math club. Very good. So you must be an expert on the problem. Anviti says two. Someone says two, and Thard says two. Okay, again, that is a coincidence. I did not intend for the answer to be two. It just kind of happened that way. But okay, let's go ahead and take a look. So, um, I think this is definitely a little easier than some of the questions because we're not dealing with crazy powers. We're just dealing with a little bit of multiplication. Okay, so when we're dealing with a sum like this, that oopsies, that was like a really terrible squiggly line. Okay, that like starts from one and goes all the way to 100. We want to use our sum formula, right? And the sum formula, it's very smart because what it does is it adds up the first and last term, and it takes the average and it multiplies by however many of those pairs there are. So that's kind of what we're going to do here, right? So in general, this summation formula is n times n plus 1 divided by 2, where n is kind of that last term. Wait. Oh, Samhith wants to explain. Yeah. Sorry, I didn't see your message, Samhith. My bad. I was like locked in. Yeah, go ahead, Samhith. Oh, if you're speaking, I'm not sure we can hear you. No, I don't think we can. Yeah, I could see you're unmuted. I've asked you to unmute, but I don't actually hear your mic, which is very unfortunate. But if you want, like, you can go ahead and put your answer in the chat, and I'll definitely read it out. Because I think you mentioned like solving this before. So yeah. Okay, awesome. I think Jason has also raised their hand. Yeah, go ahead, Jason.
Uh, I found a pattern where where it goes 1 through 100.
Mm-hmm.
Well, I've 1 plus 100 is 101, and two with 99 is 101. So basically, all that adds together is like 101 times 50.
Yeah. And actually, I think that's where we're going here. But yeah, thank you so much, Jason, for unmuting and actually sharing that really nice pattern. And the pattern that Jason has explained, is actually like kind of the premise for like where we get this formula from, right? So we're adding the first and last terms together because this is an arithmetic series, right? So like we can say these terms are evenly spaced apart. So what we're doing is we're adding the first and last terms together. Then we're adding the second and the second to last term. Then we're adding the third and the third to last term. And we kind of keep doing that until we get to the very middle. So we take the at or we take that sum from each of the pairs and multiply it by the number of numbers. But that'll actually double count our value because remember, each number is being counted twice in the pair. So we have to divide by two. So that's kind of where that summation formula comes from. I think we maybe have talked about this earlier in the course. I can't remember. But I'm pretty sure like most of you guys are familiar with this. If not, like we can stop and like talk about it a little more in depth. But yeah, okay. So that's where the premise is. And we say like 100 times 101 divided by 2 is the sum of all of these 100 terms. So that becomes 50 times 101. So then I want to take 50 times 101 um, mod 4. Okay. Mod 4. And this is basically like congruent to 50 divided by 4 is 2, or has a remainder of 2. So 50 mod 4 is 2. Sorry, that's what I meant to say. And 101 mod 4 is congruent to 3. So this is congruent to 2 times 3 mod 4. And lucky for us, 2 times 3 is super easy to do. That is 6, which happens to be congruent to 2 mod 4. Okay. So that is once again our final answer. So great work to everyone who has completed this. Okay, awesome. Um, okay. Uh, cool. Okay, I think I wrote 3, but I meant to write 1. Sorry, guys. I like totally messed that up. My bad. Okay. Um, wait, let me take a look. Okay, I think I see. All right, Bobbitt, thank you for putting a very, very nice explanation in chat in response to Coven's explanation. That is absolutely correct. So really nice job typing all that out. I think Samhith has also put in a good explanation, talking about how to find the sum and then dividing that by 4. So thank you also, Samhith, for putting that in chat. Uh, but yeah. Let's see. Okay, cool, cool, cool. So we're all on the same page here. I think something interesting to note is like, let's say I had just done like 100 times 101 divided by 2, right? And I had just done like mod 4 directly on this. So I would say like this is congruent. We know that 100 is congruent to 0 mod 4 and 101 is congruent to 1 mod 4. And we have that like divided by 2, right? So we have this like mod 4. So what we're saying is like this 0 divided by 2 mod 4, right? And I feel like 0 divided by 2 that's 0. So we have 0 mod 4. Okay, so that's super weird, right? Like, why are these two not the same? Like, why are these different? The reason is because when you're working in modular arithmetic, you cannot just divide. Like, division does not work anymore because remember, that's like the main defining operator of modular arithmetic. Like, modular arithmetic is based on the stuff left after you have remainders. So it is not possible to just like throw in another remainder thingy in here. Like, that is gonna like break the math. So, that's like one thing I would like one thing to be very careful of to ensure you're not just like doing division in your modular arithmetic because you are going to get a wrong answer. That's why I had to go ahead and do 100 divided by 2. I couldn't just do it like this. Okay? Is everyone clear like why this is not true? I think also like if you remember back to last class, I never talked about any division rule because like it breaks modular arithmetic. So that's why it doesn't exist. Okay. Um, Okay, cool. I don't see any questions about this, so let's go ahead and move on to our next problem. I think we have time for like a couple more questions. So let's see how many we can get through. Okay, that's like super tiny. Whoa. Okay. All right, so problem 4. Find the last two digits of 7 to the power of 2023. Oh yeah, this is definitely hard. But see if you can maybe make an attempt and like think about how you can do this. Well, okay. First question is, what modulus should we be working with? Like, what modulus should we be working with? Okay, I think a lot of you guys have identified what the last digit is, which is good work. Um, it definitely like narrows down like where you should be looking, right? Um, okay, so I see. Okay, NVT has said mod 7, but if we take 7 to the power of 2023 mod 7, like obviously that's divisible by 7, right? So like that's not maybe super helpful, I would argue. Something that says mod 4, but does mod 4 like cover all the possible last two digits? Like let's say I had the last digits of 23. Can I express it in mod 4? Like is that possible? Okay, so Bobbit says mod 100, and that's what I would agree with. Yeah, okay, good, good, good. So I would agree with mod 100, and the reason why, think about our place value discussion from last week, right? Where we talked about how to get the last two digits, you have to divide by 100. Because like if you think about how to get the units digit, we divide by 10. So it's kind of easy to see like to get to the hundredth digit, you have to get to the tenth digit, you have to divide by 100. Okay, awesome. So we're gonna do 7 to the power of 2023 mod 100. Um, I would say like maybe there's a couple of ways of doing this. In a case like this where it's not super easy to see any, I would say like immediate pattern, I would honestly just go ahead and try like solving for 7 to the power of 1, 7 to the power of 2, and kind of going like that, right? So 7 to the power of 1 is obviously congruent to 7 mod 100. Nothing special here. 7 cubed, or sorry, 7 squared is again also 7 mod 100. Again, nothing super special. Or sorry, 49. That's what I meant to say. Sorry, guys. My numbers game is super off today. I know I keep messing up a couple things. 7 cubed is going to be a little interesting. It's 49 times 7, which happens to be 343, but we don't care about that beginning 3. We only care about the last two digits, right? So I'm going to say this is actually just congruent to 43 mod 100. Okay, and then finally we have 7 to the power 4, which is congruent to 43 times 7, which is actually super nice because it comes out to be 301. So that's actually congruent to 1 mod 100. Okay. This will not always work out this way. Sometimes you'll have to be like, you'll go through some pretty brutal calculations. But 7 is like an interesting number. I think there are definitely some cool properties with it. I think we get very lucky figuring out that 7 to the power 4 is actually just congruent to 1 mod 100. Okay, so now that we have this thing, our problem is very simplified. We can express 7 to the power of 2023 as 7 to the power of 4, and we'll raise this value to 505, I believe, and then multiply all this by 7 cubed mod 100. Okay, we've already talked about 7 to the power 4 mod 100, so we'll write like 1 to the power of 505 times 7 cubed. Luckily for us, 1 to the power of 505 is just a very friendly one, so that's super duper nice. And so we're just left with 7 cubed mod 100, and also lucky for us, we've already calculated what that is. Comes out to be 43, which is our final answer. So the last two digits are 43. And actually, notice how this matches up because I know a lot of you guys had said the final digit was 3. This is good. The final digit we have received is 3. So that means like we're not completely wrong. And to make you sure we're right, 43 is indeed the correct answer. Okay, so thank you all to everyone who kind of put that in and also put in an explanation of how that is. I think Bhavit put in a really nice explanation in chat. So thank you, Bhavit, for just like doing such an amazing job with putting all those explanations in chat. Okay, awesome. I think we'll do like maybe a couple of different types of problems, maybe a couple more different types of problems, and then we'll end on a recent competition problem. Okay? Um, let's see if this next example. What do I like really want to do? Okay, I want to do this. I want to make sure we do this next example because I think it's a really good application of everything we talked about, and then we'll kind of pick and jump. The nice thing about modular arithmetic is there's so many cool problems to do. Like it's very, very fun. But yeah, I just have so many problems I want to discuss with you guys. But we'll try to do what we can. Okay, so our next problem is actually from the AMC 12B. It was on the 12B for me. I don't know if it was actually on the 10B. But yeah, so this next problem is what is the units digit of 6 to the power of 6 to the power of 6? I believe, oh wait, not the units digit. Wait, hold on. That was a stupid question because the units digit is obviously 6. Okay, let me think. Like, what was the question again? Will be, I need to double check this. 2025. It was a really interesting problem. I was like, oh my gosh, I just taught my kids how to do modular arithmetic. They're going to be so excited to see like you can actually use it in the AMCs. Okay, let's see. Oh, okay, never mind, never mind. It's the tens digit. Okay, here we go. Tens digit. I was like, ones digit is too easy for you guys. All right, so what is the tens digit of 6 to the power of 6 to the power of 6? Okay, a good question. Again, we're working with the tens digit, so it's definitely a little more challenging. This was on the 12B. I can't remember if it was on the 10B, because I didn't look at the 10B, but definitely an AMC problem. So now you guys can see it, like, the stuff I'm teaching you is actually relevant to competition math. In case maybe you were like, not convinced. Okay. Um, let me take a look. Okay, yeah. So everyone started putting in 6, and I was like, oh my gosh, sorry, that's too easy. But yeah. Okay, I see a lot of people saying 1. Let us see if that is correct. Okay, cool. Does anyone want to? Okay, Malvin says three. Okay, so I see a one and three. Cool. Is there anyone who like wants to share the value that they got or the answer? Jason says 91, which I highly question because I think it's very hard for a tens digit to be 91, considering 91 is not a digit. Okay, Coven. Okay, Jason says one as well. Okay, cool, cool, cool. Jason, I was just messing with you. I know what you meant. Okay, Coven would like to go ahead and share. So, Coven. Wait, I'm trying to find you in the thingy. Okay, there you go. Go ahead, Coven. Oh, wait, are you muted? Hold on. Okay, Coven, if you're talking, I'm not sure we can hear you, which is like super interesting. Is anyone else able to hear Coven? Because now I'm like very skeptical that this hearing problem has like okay, no. Well, this is highly unfortunate. I don't know why all the mics have stopped working suddenly. But Coven, thank you so much for your enthusiasm. If you want to put a solution in the chat, that would be greatly, greatly appreciated. Until then, I will go ahead and start solving this problem. This low-key might be the last question we do, but we will see. Okay, so we have 6 to the power 6 to the power 6, right? I see a lot of you guys accidentally saying like 6 to the power of 6 is 36. Remember, that's 6 times 6. We have 6 raised to the power 6, which is something entirely different. So this is definitely a beast of a problem. We have crazy exponents here. This is definitely impossible to calculate. I don't even know if a calculator could do it. So let's take a look. Do not be intimidated. So we have 6 to the power of 6 to the power of 6. And because we're finding the tens digit, we're going to take mod 100. Okay? So a couple of things we can do. That's the first thing I would do. Let me think. I don't know like what did I do to solve this problem? It's actually like it's been a minute. Okay, I would say start off by finding like patterns within 6 to the power of something. So I would say like 6 to the power of 1 is obviously congruent to 6 mod 100. Okay, nothing special here. 6 squared is congruent to 36 mod 100. Again, nothing special here. Kind of just leave that as is. Then you have 6 cubed, which is congruent to 36 times 6, which will come out to 216 or 16 mod 100. Then we get on to 6 to the power 4, which is 16 times 6 or 96 mod 100. Sorry about that. My throat is super dry. Then we have 6 to the power of 5, which is congruent to 96 times 6. Here, I will not say, like, do not multiply 96 times 6. We already know 96 is congruent to negative 4 times 6. So this is negative 24, which is actually just 76 mod 100. Okay? Um, 96 times 6 is like kind of annoying to do, so I personally wouldn't do it. And then we get 6 to the power of 6, which is congruent to 76 times 6, which comes out to be, okay, this one I would actually multiply out. I think this is going to be like mod 5600, or 56 mod 100, sorry, I like said that backwards. Okay, and then 6 to the power of 7 is congruent to 56 times 6, which is congruent to, I believe this is 16 mod 100. I think that's correct. Yes, I think I did that right. Okay, so a couple of reasons. Like, why did I continue to keep going when it's like, why did I go all the way to 7 to like figure out this pattern? It is not because I knew the pattern would repeat every 6 values. Like, no, 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 this is not true. The reason why I know this um, is because I see a lot of like odd tens digits, right? I start off with like 3 and then 1 and then 9 and then 7 and then 5. And the fact that it's all odd like kind of leads me to believe like, okay, maybe there might be a pattern, like maybe it ends in sight. So that's like kind of why I was convinced to stick it out. Now, if I had gone through and I had seen some of the same numbers like 3 or 4 times, like maybe I would have been like, okay, this is hopeless. There's no pattern. I would have stopped and like try to find a different approach. But because I see like the pattern of odd numbers kind of cycling around, this is like an indication like, okay, there might be a pattern, so let me try to stick it out and see if I can get the same value. So in this case, our pattern would kind of be like 31975, 31975. Okay? Um, yeah. Oh wait, actually, hold on. Is one gonna be in this pattern? I don't think one, or sorry, I don't think three is gonna be in this pattern. It should just be like 1975, 1975. Okay, so it like kind of repeats in a cycle. Uh, four. Wait, I definitely hold on. Sorry, guys. I think I like mixed up the last value. Wait, okay, hold on. This last one is not supposed to be 1, 6. It's supposed to be 3, 6. Okay, yeah, that's where I like figured out something was wrong. Okay. Yes, this is a difficult problem. It is a difficult question. Yeah. Sometimes like I'm in a different like mindset in the competition. And then I like think back on how I solved some of these questions. I'm like, wow, that's like crazy that I did that. This is one of those cases. Okay, so this is 16 100. Okay, sorry about that. So this is where we go. So the pattern is gonna be like 3, 1, 9, 7, 5. And then you kind of keep going. So notice how it goes like that. Okay, cool. Okay, so I think Malden said answer 3, which might have been based on like what I had previously done. But thank you, Malden, for actually putting in the initial answer. Okay, so we know like 6 to the power of so we see like there's a cycle of 5. That's good. That's really nice. So what we need to figure out though is like what are we gonna do with like this 6 to the power of 6? So we're gonna do 6 to the power of 6 mod 5 to even figure out like where are we standing in this case. And so we can figure out like 6 to the power of 6 is like obviously congruent like to 1 to the power of 6 mod 5. Okay, so this is congruent to 1. Oh, wait, I like missed mod 5. Oh no. So this is congruent to 1 mod. Okay, so that's where like all of this comes from. That's where the cycle in the kind of top part comes from, this numerator thingy. Okay, so then we will say that, let's see, 6 to the power of 6 to the power of 6 is going to be congruent. Let's see. It's going to be like that first value. So it'll be 6 to the power of, right? Okay, hold on. Let me double check this. Hmm. Okay. Let's see. Oh, okay. I think I know where I went wrong. So the one thing to note is this first term is actually like not going to matter, right? Because like we don't use the first term again. So here's what I'm going to do. I'm going to say I'm going to erase all of this. So we missed one small thing. The fact is, like, we have 6 to the power 6, which is correct, but we have to subtract 1 for that initial term of 6 to the power 1, because that's not going to count. This never occurs in our pattern, so we have to subtract 1 to account for that. So we're going to do 6 to the power 6 minus 1 mod 5, okay? And that's going to be congruent to 1 to the power 6 minus 1 mod 5, which is going to be congruent to 0 mod 5, okay? And so this handles like this first initial bit. So then we get like 6 to the power of 0. So we need to figure out like what's the 0th place in our pattern. So like that should basically be our last term. So we go to, if we look at our pattern, we said our pattern was 3, 1, 9, 7, 5. So the last term in our pattern is 5, and that is the tens digit. Okay, so it has been a week since I last did this, or like close to a week. So like, let me re-explain this because I was also figuring this out alongside you guys. So in case this was confusing, let me go through a quick explanation of like what happened here, okay? So a couple of things. I realize like I should not have written all of this in red, but what's done is done. Okay, so starting off, what I'm trying to do is I'm trying to find a pattern like I do in any like typical modular arithmetic problem. I'm finding a pattern in this case because I don't see like any obvious way to simplify like 6 to the, like I don't see any obvious way to simplify this. So what I'm going to do is find this pattern. I start off with my 6, and then I go to 36, and then I go to 16, and then 96, and I keep doing that. And the reason why I'm sticking it out so long, even past 5 terms, is the fact that like I'm starting to see some odd numbers. And this is typically a clue that like there's probably some pattern here. If you're dealing with a lot of like odd numbers, that seem to go like 1, 3, 5, 7, 9, something like that format, there's probably like a pattern there. So if you're dealing with modular arithmetic and you're getting these values in the tens digit, units digit, whatever, stick it out until you maybe start seeing some repetition. Okay, so that's kind of what we did here. Like that's the motivation for like why I went all the way down here. So we'll see like 6 to the power of 2 is congruent to 36 mod 100, 6 to the power of 3 is congruent to 16 mod 100, and we kind of keep doing that. Also notice how I use like each of these terms to do like the next one. Even though 6 to the power 4 is way bigger than 96, the last two digits are 96. That's all we care about. We don't care about the rest of those digits. So that's kind of like where we're going here. And so we get to 76, we get to 56, and once we reach 56, we repeat back to 36 again, and we kind of keep going on like that. And so here's where our cycle is. It's going to be consisting of um, these terms. So the cycle repeats every 5 powers. But the important thing to note is we don't start at the power of 1. We start at the power of 2. So everything that's like congruent to 2 mod 5 is going to have a units digit of 3. Okay? Or sorry, a tens digit of 3. Everything that's congruent to 3 mod 5 is going to have a units digit of 1. And you kind of keep going like that. So it's definitely going to be a little different. So you have to kind of subtract that 1 to account for the rest of these values, okay? So I have 6 to the power of 6 to the power of 6. So this is like my exponent. Okay, this is the part I care about. Wait, I like wrote that really badly. So I need to figure out like, is this going to be like congruent to 2, 3, 4, 5, or 6? Okay, so that's what my goal is. So what I do here is I have 6 to the power of 6 minus 1, right? Because I'm not considering this first term with 6 to the power of 1. Because this is not included in my pattern. This is not repeating at all. I need to exclude that so I can run my pattern of 5. Okay, I can run my cycle of 5. So that's why I do 6 to the power of 6 minus 1. Okay, and then I take mod 5 of that. Now we know 6 mod 5 is just 1, so that's why I replace this base of 6 with 1. So I get 1 to the power of 6 minus 1 mod 5. 1 to the power of 6 is just 1, right? So 1 minus 1 is congruent to 0 mod 5. So this is actually going to be like the last term in our cycle, right? So we go 1, 2, 3, 4, 5. That fifth term, 6 to the power of 6, has that value of 5, okay? So that's where that units or that tens digit is going to go. Okay, if that's not clear, let me know in the chat. And while you guys put your questions in, I'm going to go ahead and take a look at some of these questions. Okay, I think Audie asked, can't you just use the 31975 pattern and convert 6 to the power? Okay. So Audie, the reason why you can't do okay, yeah. So I think we talked about this a little bit earlier. The reason why 6, okay, so this is not 36. That's like super clear. Or that should be clear because this is not 6 times 6. It is 6 raised to the power of 6. Okay? So that's why like you cannot just say like this is equal to 6 to the power of 36. So that's not going to lead you to the correct answer. Okay? I think that's like where the premise was based on. So that's kind of like why we can't apply that. And then also, because we get a remainder of 0 mod 5, that means the cycle is at its like very end, right? So it's like just finishing and then it's about to restart at the beginning again. So like if it restarted at the beginning, it would actually be 1. So this would actually be 1 instead. Yeah, that's how it should be. Yes. Actually, if we had done what I did before. Wait, actually, no, I don't want to go down that route. That route is like kind of messy, so I'm not gonna do it. Never mind. We'll do it like this. I don't think this is how I actually solved it in the contest. I remember doing something different, but I guess this is also another solution. So yeah, this is a real AMC 12B problem from 2025 AMC 12B. So it's okay if this is challenging because it is for meant for juniors and seniors, which are like who are like years older than you guys. So if you guys need me to like re-explain a certain part, or you're just super lost with something I said, please let me know in the last couple minutes we have, or the last couple seconds we have, so that way we can talk about it. But I think this is a good question, and it kind of shows like why you can't just rely on like patterns entirely. Okay? Awesome sauce. So if you have any questions, go ahead. What question number was this? I think this was like question 9. But if it was on the AMC 10, it probably would have been like 13 or 14, I would say. Okay. Audie, you asked if it should be 3. Do you want to maybe put in like what your justification is that? Because I explained a little earlier, like the reason why it's 5 and not 3 is because when you have 0 mod 5, you're at the very end of your cycle, right? This is the 5th term, which is like congruent to 0 mod 5. That's how the patterns will work when you're doing it like that. So that's why it should be 5. If it was like maybe 1 mod 5, then I would agree with you that it's 3. But because it's 0 mod 5, that corresponds to the last term or the 5th term. Okay? Awesome. Alrighty. Okay, I don't see any other questions, and since it's 9 o'clock, we'll go ahead and end for now. I will see you all next week. If you guys are here in algebra, or sorry, if you're here for geometry, we will have a class on Monday, the coming Monday, when you guys are probably on Thanksgiving break. We will not have class next week for algebra, so please enjoy like your break. Have some time like with your family and enjoy like eating good food. And then we will pick up our last week of classes after Thanksgiving break. So that'll be the last time I will see you all. Okay. So thank you all so much for our second to last class. I hope you had fun. I hope you learned something new. And I hope you guys are very proud of yourself for working with these extremely difficult topics. On that note, I will see everyone next week unless there are any questions. But as always, feel free to reach out to me through email. Alrighty. Bye, everyone. Bye, Tombi. Bye, Hitharth. Bye, Samhit. Bye, Jason. Bye, Rohan. Yeah, bye, Coven. Ooh, that's awesome, Bobbit. Have fun. Yeah. Bye, Marvin. Bye, Coven. Bye, Anviti. Thank you so much. Bye, Nahal. Awesome. Alrighty. Bye, Mari. Thanks so much for joining.